What does all this abstract theory have to do with time travel? What is the relation of it with time travel? The link can be found in Einstein's most famous thought experiment, the twin paradox. Have you heard about it? Since there are no twins in Back to the Future movie, let's use the Olsen twins as an example. Marty Kate Olsen and Ashley Olsen share the same frame of reference while shooting a space-age film together on Hollywood set. Here is the picture of these actresses. But there is a twist. When Marty Kate returns to the set, she will have aged more slowly than Ashley because time passed more slowly for her than it did for her twin sister. Her watch will show that it took less time for her to go and return than Ashley's watch will show. In that movie, Ashley stayed in the world and the other one moved to the space, okay? After turning, Mary Kate returns to the set. She will have aged more slowly than Ashley. She will be younger because time passed more slowly for her than it did for her twin sister. Her watch will show that it took less time for her to go and return than Ashley's watch will show. According to what we have learned so far, when Mary Kate and Ashley once more share the same frame of reference, the effects of time dilation and length contraction disappear. It should disappear. Their watch should be in synchronous. So what happened here? At some point, Mary Kate turns around for the return trip. In so doing, she switched frames of reference from one in which she is moving away from Ashley to one in which she is moving toward Ashley. That action breaks the symmetry between them so that they are no longer in synchronous when Mary Kate returns to her sister frame of reference. That's why, in reality, Mary Kate will be younger than Ashley. Mary Kate gained only a few fraction of a second, but technically she returned to the future. As you see here, you can go to the future by means of relativity. So it is reasonable that someone could travel into the future by moving at faster and faster speeds. The bad news for time travelers is that it's almost impossible to travel into the past. This is the bad news. Let me explain it a little bit more. In order to do so, we would need to travel faster than speed of light. To manage that, we should travel faster than the speed of light, but it's impossible. And not even Doc's modified DeLorean could manage that. In the movie, it can do it at 88 miles per second, but it's a movie. Light sets the cosmic speed limit. It is believed to be the highest speed at which an object without mass, for example, such as a photon, can travel at that speed. If something has a mass, it's impossible. An object with mass like Marty can never reach the speed of light. That's because an object's mass will increase as the speed increases. Marty will get heavier the faster he goes, and the amount of energy required to continue accelerating will increase proportionally. An object's mass becomes infinite at the speed of light. It means you need infinite energy to reach that speed. So it would require an infinite amount of energy to reach the full speed of light. Let's say he finds a source of infinite energy, for example. What happens? When he reaches the speed of light, he would contract to nothing. Why? Because it's due to the length contraction. Its length will be 0. Marty would shrink to a wafer-thin, two-dimensional version of himself and possibly wink out of existence. He would die. It's not possible that he would survive at the other side of the speed of light barrier. There are other more philosophical complications also. Just after his arrival in the 1950s, Marty accidentally meets both his parents and accidentally keeps them away from each other. This event results his existence into question. unless he can correct the anomaly. It's a postmodern twist on the grandfather paradox. Let me talk about grandfather paradox a little bit. If someone traveled back to a time before he was born and killed his own grandfather, what will happen? Then how could that person be alive to travel back in time and kill his own grandfather? It's a contradiction. If traveling into past were possible, we would be able to rewrite history, but there is no guarantee that our near future will be an improvement. In the real world, physicists have developed another way of explaining such paradoxes, the notion of parallel universes. According to one theory, of course, it's still an idea, there may be an infinite number of universes. When Marty prevents his parents from meeting, he does so in only one universe, which is no longer the universe he exists in after that. Marty finally corrects the life-threatening paradox at the end and makes sure his parents get together, but he still irrevocably, inevitably alters the future. When he returns, he finds his father a confident, successful novelist, his mother youthful, slim, and healthy, his brother a successful broker, and his sister is a cheerful and attractive. He made decisions and altered outcomes, fortunately for the better. In so doing, he created a new universe identical to his own up until the time he changed the original succession of events. As a result, as a last word, we may not have Doc's magical DeLorean, but we do have Einstein and special relativity. By that token, we are already time travelers, because each of us is always moving through both space and time. And perhaps somewhere in parallel universe, the laws of physics let scientists to overcome the barriers to time travel in either direction. Our parallel self is merely hopping back and forth among the centuries, unlocking the secrets of both the future and the past. Thank you for listening to my presentation. Thank you, everybody.
Okay, I think so. That was great presentation from Cemalettin Karapıçak, who is one of the famous and valuable scientists in Turkey about the physics. And that was a great presentation, as I said. I don't know, the Back to the Future contains a lot of scientists think. It was very interesting, right? Thank you very much, Mr. Pasupati. Thank you very much. So we will move to INTOC Curious Science right now, and there will be 3 most successful students from Turkey, which is one of them came from the Bilkent University and one of them came from the METU, and we said about that already. It's one of the most successful universities in Turkey. So firstly, Boray Güvenç and Ulaş Mutlu will talk about the golden ratio, and after that, Emre Geniş will talk about the journey of the sunlight. So I want to keep it short. Let's hit you guys. Welcome. That guys are ex-students, right? Thank you very much. Okay, let's move to the Curious Science. Boray Güvenç and Ulaş Mutlu, we are listening to you.
Okay. First of all, hi everyone. Greetings from Turkey. But first of all, could you share with? We are not host right now.
Host. Let me make you host. Wait. Yeah, you are the host right now.
Okay, thanks. Okay. Are you able to see our presentation right now?
Yes, yes.
Yes,
Okay.
yes, we can.
Yeah, we can see it.
Okay.
Hi everyone. Again, as our dear teacher mentioned before, my name is Bora and my friend's name is Ulash. And today our topic names is the golden ratio, which is the number of the beauty. First of all, my dear friend Ulash will talk about what's golden ratio. Let's begin.
Okay. The golden ratio, as known as the divine proportion, is one of the famous irrational numbers like pi, and it firstly described by Euclid almost 2,500 years ago, and this ratio is related with beauty, aesthetics, and symmetry in our life, and it can be explained by some mathematical explanations. And right now, my dear friend Boray will explain the first explanation of this ratio.
We can explain the golden ratio with Fibonacci sequence actually, and this is really famous sequence, and lots of people know about something about this sequence actually. There is a famous picture which is the golden rectangle. We will talk about it later in our presentation, and if we write some numbers in these squares, we will see these all numbers are the Fibonacci numbers. And if I explain these numbers better, there is an easy rule about Fibonacci numbers. Okay, if we add 0 and 1, we will achieve 1. And there is our second calculation. And if we take 1 and add 1 again, we will achieve 2. And right now I will explain the rule about it. If we take last two Fibonacci numbers and add them together, you will achieve another Fibonacci number. Like you can see there, 1 plus 2 is equal to 3. And in the next equation, if we take 2 and 3 and add them together, we will achieve 5. If you continue doing like that, 3 plus 5 is equal to 8, and it's goes like that. Okay. But what's the connection between Fibonacci numbers and the golden ratio? As can be seen, there are Fibonacci numbers. And if we take one of those numbers, for example, if we take 233 and select the previous Fibonacci number, which is 144, and divide these two numbers, you will approximately achieve the golden ratio, which is 1.618. Okay, right now, Ulash will talk about another perspective about the golden ratio. Continue, Ulash.
As I said, there are two explanations of this ratio in mathematics. Right now, if we consider a line with two parts, which one B is short and A is long part of the line, and if we add them together, we achieve A plus B, and if we divide this addition to the long part of this line, which is A, we will achieve a golden ratio, which is 1.618, and also it can be explained by a letter, which is a Greek letter called phi. And if we, as Boray said, if we consider a golden rectangle, and if we try to add the Fibonacci numbers in the golden rectangle with parabolic lines like this, we will achieve a golden spiral, which can be observed in nature. Now you can see some example of this golden spiral, and isn't it beautiful, Boray?
Yes, really, it is. Okay, I will continue with golden ratio in arts, designs, and architecture. First of all, everyone knows Leonardo da Vinci and his famous drawing, Mona Lisa. And actually, he used golden ratio in his drawings, actually. And he changed the name of the golden ratio as divine proportion, and he used this proportion in his drawings, as can be seen in this picture. And there is another famous drawing of Leonardo da Vinci, actually, its name is Vitrine Man. And this picture illustrates that the human body is proportionate according to golden ratio, the divine proportion, actually. And there are lots of companies in the world right now, and they are using golden ratio in their logos. And there are some examples about it. For example, you can see Pepsi, National Geographic, Twitter, and Apple logos. And right now, Ulaş will continue with architecture.
As I said before, a Greek letter phi, it came from the architecture of this temple, which is called Parthenon temple. And this Greek letter, golden ratios, Greek letter of phi, came from the architecture of this temple, which is Fidas. And there are some example of golden ratio with in some architectural structures. Right now, my dear friend Boray will continue with golden ratio in human body.
Actually, we said that, that you can see golden ratio in everywhere, actually. And there are some examples of golden ratio in our body. If you calculate those lengths and divide those lengths, you will achieve a golden ratio, but not exactly. It will be approximately, actually. And there are some examples of the golden ratio in our body. If we divide length of the face with wideness of the face, we will approximately achieve golden ratio. And there are other examples. If you are interested in this topic, you can try. Yes, yes.
So there are too many examples of this ratio in nature. Now you can see some example of golden ratio with golden spiral in some flowers and natural stuff. There is a sunflower, another flower, and you can observe the golden spiral in these pictures. You can see if we add the seeds of the sunflower, we can achieve a golden spiral. And also, I will be explain another fact about the golden ratio, why this ratio is so common and why is related with us. This ratio help human race they maintain their species with natural selection. Our ancestors managed to survive in nature with memorizing their some symmetric and asymmetric structures with golden ratio, and this ratio helped us to survive in nature. And today we consider the golden ratio as a standard of beauty and aesthetics, and it can help us in many fields like engineering, design, creating art. And that's all for us right now.
Thank you for listening our presentation. Again, greetings from Turkey. And right now we are going. Yes, goodbye.
And also our dear friend, another friend, Emre Geniş will present his presentation about journey of sunlight.
Okay. Thank you very much for this great presentation to Boray and Ulaş, which was nearly perfect. So we will move to the Emre Geniş, and he will talk about the journey of the sunlight right now. Emre, are you there?
Yes, I am.
And
Yeah, okay.
hello everyone.
Hello,
Um,
Emre. Now I'm making you host, which is you are already host right now. You may start your presentation if you want. Stage is yours.
let me share my presentation. Is there anyone can see? Or anyone can see?
Yeah.
Yes, yes, we
Yeah,
can.
we can.
Let me start. Hello everyone. I am. My name is Emre, and I'm from University, which is Metro. And my presentation's topic is how long does it take sunlight to reach the Earth, or we can say the journey of the sunlight. So let's begin with. As we know, it's a kind of strange question, but we need to think about it to use that clean energy for everything. Sunlight travels at the speed of the light photons emitted from the surface of the sun, and sun need to travel across the vacuum of the space to reach our eyes. To understand that, let's calculate it. Here's the math. We orbit the sun at the distance of about 150 million kilometers. Light moves at 300,000 kilometers per second. Divide these and you get 500 seconds, or 8 minutes and 20 seconds. This is an average number. Remember, the Earth follows an elliptical orbit around the sun, ranging from 147 million to 152 million kilometers. At its closest point, sunlight only takes 490 seconds to reach Earth, and then at the most distant point, it takes 507 seconds for sunlight to make the journey. But if you calculate the timing of it, one sunlight reaches an average of 8 minutes and 20 seconds from sun to the Earth. Nevertheless, is it enough for us? Of course not. As we know, sunlight needs to be occurred. Now, our question about how long a sunlight is occurred. Photons are produced by the nuclear reactions deep on the core of the sun. As photons flows out their core, they interact with matter and lose energy, becoming longer wavelengths of a light. They start out gamma rays at the core. This is the sun's core, and they start at a gamma rays in the core, but end up as X-rays, ultraviolet, or visible light as they near as the surface. So why? Each photon travels at a speed of 300,000 kilometers per second until it collides with a proton, and it's wired in another direction, acting like a bullet writing of every charged particle it strikes. This is like a random walk problem right now. The answer is given by this formula. As you see, the energy comes and they collide with the protons, and they just like pretend as a bullet. Distance equals step size times the square root of the number of steps. For example, if you are taking a random walk from your front door with 1 meter stride each second, it will take you 1 million steps, and 11 days equals 39,600 seconds just to travel 1 kilometer. Mass of the sun is 1.99 time 30 power of 10 power of 30 times kilogram. We can use that for calculate the number of protons on the sun. Let's assume for a second that all the sun's protons are evenly spread out, making the average distance between them about 1.0 times 10 power of minus 10 meters. This is the distance of the protons. To random walk the 690,000 kilometers from the core to solar surface of the sun. Let's assume that it's the core of the sun, and this is the surface. It's this distance is 690 kilometer, 690,000 kilometer. That would require 3.9 times 37 power of 10 steps, giving a total travel time of 400 billion years. But our calculation is wrong. As we know, the sun is only 4.6 billion years old. So what happened? The sun isn't actually of uniform density, and photons may miss quite a near
protons between every collision. Sun has a hot core where the fusion reaction occurs. Surrounding that is the radiative zone, followed by the convective zone, which extends all the way off the surface. The material in the core is much denser than the lead, as you see. Protons are much denser. Protons are most denser at the core zone. Radiative zone is the less denser than that, and convective zone is less denser of that. When we use a computer as a sophisticated solar interior model to calculate the random walk equation with these changing quantities, it speeds out of the following number: 170,000 years. Not that long, huh? The light needs 107,000 years plus 8 minutes and 20 seconds to hit our eyes today. As you see, this journey of the light is times 170,000 years plus 8 minutes and 20 seconds to reach the Earth. The light you see from your computer is nanoseconds old. The light reflected from the surface of the moon takes only a second to reach the Earth. The sun is more than 8 light minutes away. And so, if the light from the nearest star, Alpha Centauri, makes more than 4 years to reach us, we are seeing that star 4 years in the past. There are galaxies millions of light years away, which means the light we are seeing left the surface from those stars millions of years ago. For example, the galaxy M109 is located about 83.5 million light years away. If aliens lived in those galaxies and had strong enough telescopes, they would see the Earth as it looked in the past. They might even see dinosaurs walking on the surface. They probably see you like this, like a dinosaur. Thanks for the listening, and let's continue with another presentation.